Yeah.
Okay, great. Right, so I'll just start. So good afternoon, everyone. My name is Anish Agarwal. I'm a PhD student here at MIT, advised by Alberto, Devavrat, and Munzer. Today we'll be talking about causal matrix completion. This is joint work with Munzer, Devavrat, and Dennis. Dennis is now at Berkeley, but the work was primarily done when we were all at MIT. So let me just give, for those of you who do not know what matrix completion is, a quick overview of what it is. So the canonical motivation for matrix completion came from recommendation systems. So here you can think of having, say, m rows corresponding to m users and n columns corresponding to n movies. And you get a very sparse subset of the entries being observed. So for example, you can think of, let's say, Netflix and some person rating it 1 to 5, right? And most of these things are missing. Are missing. And for the things you observe, we assume that they are observed with noise. So this is kind of how a matrix looks like. Hopefully at the end of the talk, I'll convince you that there are many more interesting applications of matrix completion over just recommendation systems, that remains a canonical use case. So a quick overview of the model. So the goal in matrix completion is to fill the missing values and denoise observed values. So we say there's a ground truth matrix, it's called A, with m rows and n columns. And what you observe is Y. Okay, so Y is somehow related to A for some entries that you do observe. The entries that you do observe are given by the matrix D. So you can think of D as a matrix of zeros and ones. If D is 1 or Dij is 1, that means Aij is noisily observed, given by Yij. If D is 0, then you don't observe, it's missing, corresponding to star. So the goal is, can we recover A hat from Y and D, which is your sparsity matrix, your mask, and the observations, such that A hat is close to A. And there are many ways of defining what close is. So you could think of the canonical ones are, say, the Frobenius norm or the operator norm. There are other more interesting norms that have been showing up recently, such as the to infinity, which is, let's say, the maximum error over any particular column, or the infinity, which is the maximum error over any particular entry. Right, so. Okay, so that's a quick overview of what the goal of matrix completion is and how data looks like in matrix completion. So now I'll give you the model that we'll work with and a quick literature review of the types of models people have been thinking about and type of results they've been able to show so far. So this is, in some sense, every work you see will essentially have this kind of model for A, which is a ground truth matrix. So Aij, which is the ith row and jth column in expectation, Aij is some function of ui and vj. Ui is a latent factor associated with row I, vj is a latent factor associated with column j, and f is some latent function. We can normally assume it's smooth in some sense, like it's wholly continuous or it's Lipschitz. Here, for the rest of the talk, we're going to assume that it's basically low rank. So what that means is it's bilinear. So ui transpose vj gives you aij. Okay, and r is small in some sense. So r is going to be a lot smaller than the latent dimensions of m and n. And that's going to be the key structure we assume about A to be able to learn across the different entries of this matrix. Cool. Now, what's the model for noise? So we're going to assume, so we need to connect Y, which are observations, with A. So we're going to say Yij is equal to Aij plus some epsilon ij. Okay? And that basically can be thought of as noise or the randomness in the entry. And it means 0, so basically the expectation of Yij is going to be Aij. Right, and of course the noise distribution can vary across entries, right?
So
because
0 for each observation.
For each observation.
So in the next case, you have 1 to 5.
Mm-hmm.
5 is the highest.
Yeah.
How can that be?
So you can think of the 1 to 5 as being some integer observations of some underlying continuous process. For example, think of it like a Poisson, or let's say like a censored Poisson, which has limits of 1 to 5. And that's a continuous parameter, and then you're observing a discrete instantiation of that continuous parameter.
Okay.
Or think of, let's say, think of a matrix of values from between 0 and 1, and so think of that as a bias of a coin. And then if you observe that entry, you're observing a flip with the probability Pij being the probability head or probability tail. Okay, so now those two things are pretty standard. Every paper you see in matrix completion is going to assume something like that. Now, where it gets interesting and why I'm calling this causal matrix completion is because of the model of missingness. That's where it gets interesting. So A is the signal matrix that we're trying to recover. D is the observed matrix, which determines which entries are missing and which are observed. Right? I think the key question is A independent of D? Right? So this is what we're going to explore for the next few slides is under what conditions are these two things independent, and what kinds of things have people been able to say depending on the correlation between these things.
Yeah. Sorry, actually, just to follow up on Alberto's question, actually,
Yeah.
before we leave the noise piece behind entirely. So should I be thinking of AIJ here as stochastic or non-stochastic?
Non-stochastic.
Non-stochastic.
Yeah.
And so if I were in a stochastic world, this would say that epsilon ij is conditional in 0 given I.
Yeah, absolutely.
Okay.
Yeah. Yeah, great. Thank you. Okay, so this is the way my terminology that I'm going to introduce for missingness. It builds very heavily off Don Rubin's terminology for missingness. So he has the same thing, missing completely at random, and I'll explain what that means. Then he has something called missing at random, and then missing not at random. I'm going to put missing at random as a special case of limited missing. Sorry, this is a mistake. Limited missing not at random, and then we'll talk about another missingness model that we'll explore in this paper. Okay, so let's start with missing completely at random. So this is the canonical model that people use in matrix completion, at least in statistics and machine learning. That's the model people use. And the idea is that each entry ij is observed with probability p greater than 0. One way of thinking about that is that the matrix D is such that expectation of Dij is p. And that whether you see it or not is independent of everything else in your system. Right? So you can think of you as having like n times m independent experiments. Probability that the outcome of the experiment is revealed is p for every entry. Right? And then this has been very popular in statistics. So you can think about the question that the game people play is how small can you make p, and then the structure you place on A. Right? So how low rank can it be? And then as a result, how small can P be, and so on and so forth. So those are the types of questions people play. And this literature is massive. It's been, I think it started with Terence Tao and Candace many years ago, and then it's just kind of blown up, and it's been incredibly interesting. So I think, but at a high level, there are three kinds of methods, I'd say. There's the spectral methods, where you kind of look at the spectrum of the observed matrix, and then you somehow find a low rank approximation of it by looking at the spectrum. And so one popular method there is universal single value thresholding by Saurav Chatterjee. It's published in the Annals of Statistics. And I think that's been like the canonical method that people look at when they think of spectral methods for matrix completion. Then you have optimization-based methods. So you kind of do something like nuclear norm minimization of the matrix, which kind of induces sparsity. So you can think of that as a matrix analog of the lasso in some sense. And there's a lot of different methods. One of the most popular is something called soft compute. And essentially it's some play on nuclear norm minimization. And there's a lot of works that explore this, such as Candace and Recht, and then Hasty, Mazunar, Izade, and so on and so forth. And another class of methods is nearest neighbor methods. So that's what people call collaborative filtering. And the idea being that you look at other people that are close to you in some sense, and you use that to impute entries that you haven't seen. And we'll explore that in detail in a second. I think it was first came by Goldberg in '92, and has been explored by a variety of people, including Dave Rath and his co-authors in 2018 and 20. And so I'll do this very, very quickly. So this is just kind of I guess, a scorecard of what people have done so far for different kinds of algorithms. Pretty much every result so far has been around Frobenius norm recovery. So you ask how close is A hat to A on average over every entry of the matrix. Okay, and the types of results you have are basically you want a result that looks at the form n, which is, let's say you have an n by n matrix. So let's say the number of rows and number of columns is the same. You don't want it to scale as n squared. You want to scale basically linearly in m, or at least much smaller than n squared, and then some polynomial function of r. And so all the results you have look something like that, right? It's the n times some function of r, and the polynomial in n is hopefully much smaller than n squared. That's kind of the key takeaway. And then generally there's been a significant lack of results on, say, Gaussian approximation or asymptotic normality that helps you produce your confidence intervals. It's recently happening. There's been one paper by Junking Pan at Princeton as co-authors, which is published in PNAS, I think. So it's coming, but it's been generally lacking. Okay, and then the nearest neighbor methods, I'd say, are the only ones that have an infinity norm bound on them. So they're producing a bound for every particular entry. And that makes sense because inherently it's a local method. So it's producing it's imputing every entry one by one rather than this global method that the rest of these things are. Okay, so that's a tour of missing completely at random. So 20 years of work in 2 minutes. Now we'll do limited missing not at random. Again, apologies for the typo. So first we'll start with limiting missing not at random with covariates. So this is what Rubin would call something like missing at random. So the difference now is that you allow more generality in the sense that each entry ij, rather than being observed with probability p, is now observed with probability pij. Okay, so the probability of an experiment happening for entry ij can be different for different entries, but it's still independent of everything else in the system. Okay, and then you have a positivity condition, which is a minimum of pij is less than or equal to some, say, p star. Right, and basically every result you see in these works will scale as 1 over p star, something like that. Right? And the next thing they assume access to is covariates. So some covariates associated with rows and some covariates associated with columns. So like, let's say the genre of a movie or some engagement levels of a user. And they use that essentially annual matrix D to learn PIJ. I'll go to that in a second. But basically assume there's some function, say a logistic function that maps your covariates to PIJ. That's the model. And so then here's the algorithm that they do. They look at your covariates xi and xj, and then they use that to fit sigma hat, which is the thing that maps the covariates to your probability of observing an entry. For example, using logistic regression, then you get p hat ij from that. Then what they do is they run a reweighted MCAR algorithm. Right? So they reweight either the entry itself or the loss function associated with that particular entry. So rather than it being yij, you'll do yij over p hat ij. And that can be thought of as some form of inverse propensity weighting. Right? And then they run MCAR again, basically with this reweighted, so it's kind of debiased in this way. And there's a collection of papers that have come out thinking about this. So Schnabel et al., I think they're at Cornell, and then Little and Rubin in 19 have been exploring these kinds of methods to debias matrix completion if you have if you have access to covariates. Any questions? Okay, and so what is let's just say what I think is the problem with the previous one is that you had access to covariates. Now there's a lot of recent work over the last year which has been saying, okay, so let's assume the same thing, which is that each entry is observed with probability pij. The positivity condition is p star, it's the same. But now we can assume latent structure in D itself. So we can assume that expectation of D, call that P, is low rank. Okay, so there's an inherent structure in the P's themselves. And so they don't assume access to observed covariates. This is what I call limited missing not at random without covariates. And so it's a pretty cute algorithm. So now what you do is you run your favorite MCAR algorithm on the matrix D. So that can be thought of as a matrix of ones and zeros. You use matrix completion to learn p hat. And that's one thing I'd like to say is that matrix completion, a lot of times people think about it as simply filling in missing entries, but it's more than that. It's about denoising as well. Right? So this is what I mean with the D's can be thought of as like ones and zeros, and you're trying to learn the underlying probabilities P using whatever MCAR algorithm. And then again, you do the same thing. You reweight your entries Y with the learn P hat IJs, and then you have your estimate Yij. Right? So you're basically running MCAR twice to get your estimate.
I thought before there was this distinction between matrix completion and matrix estimation, and matrix completion does not denoise and matrix estimation denoises.
So I think they're just different terminologies. I maybe loosely use matrix completion. So I use matrix completion for both of them. They've not used the matrix estimation for one of them.
Yeah, so I have an opinion there. Okay, it's not that I was trying to learn if I was confused.
Yeah.
And I do agree with your question.
There's a constant debate there two of us have. So this has gotten very popular, this idea of using matrix completion twice. And it's been explored again by Saurabh Chatterjee and Bhattacharya. It just came out like a month ago. And then David Bly and his authors in 2020, and George Chen, who's Devar's ex-student, who's at Carnegie Mellon. And the first result I've seen, at least in asymptotic consistency, has been by Chatterjee, which happened recently. So as a summary, what is the limitation of the current models? So one is you have to, each entry is observed with probability Pij, with missing complete random Pij equals to P, and it's independent of everything else in the system. Right? So it's kind of an experimental setup, the model that they use. Second, they assume that things cannot be missing. There's a low bound on observing a particular entry given by P star. And then either you have access to observed covariates, or somehow the expectation of D is nice, like it's low rank or something like that. And so those are the three key assumptions that everyone makes thus far. That's why I call it limited missing or random. So, okay, so is there a reason to worry about the missingness model? So we're going to show you a simulation that hopefully convinces you that it is. So this is a simple simulation that we ran. So here we kept the number of rows and the number of columns to be the same, m equals to n equals to 80. And we create three different models of missingness. So mcar, where we just had everything observed with probability like 30%, something like that. Then limited mnar, which is where each entry has a different probability of it being observed and has that low rank structure and the way these are observed. And you can kind of see it starts looking something like this in the second pane here. And then what I call causal mnar, and I'll explain what that means in a second, is where where we break the conditions for limited mnar. In particular, there is a zero probability of seeing certain entries. The probability of seeing one entry affects the probability of seeing another entry, and it's not a low rank matrix, right? So we're breaking the key assumptions needed for the algorithm so far. So let's see, at least empirically, does that affect anything? So let's start with mcar, okay? And I'm going to give you three different, okay, so the first plane here, in light blue, what you see is the distribution of true ratings. We created ratings from 1 to 5, like Netflix. And so the light blue is the distribution of true ratings. And then the dark blue is the ratings that we get to observe as the algorithm. And you can see under mcar, as you'd expect, the distribution of true entries of the true ratings and the distribution of the revealed ratings look like each other, right, up to a scaling. Right, they have kind of the same nice curve. And then we ran three algorithms. So the first one is universal singular value thresholding, which is kind of state of the art for spectral methods. Then we ran soft compute, which is state of the art for optimization-based methods. And for those of you who are familiar with the work of Athi and Imbens and Bayati and all on the causal panel data stuff, basically what they're running is soft compute. That's what they're analyzing. And then this method that we proposed, which is called synthetic nearest neighbors. I'll explain that in a second. So what we did is, given the dark blue ratings, we ran it through these three different algorithms and saw how well could it recover the light blue distribution. Okay, so you see that USVT starts performing pretty terribly already. It's getting the mean right, but not the distribution. Right? It's kind of centered, squished in. Soft compute is doing beautifully, kind of matches. You can't even see the light blue. It's kind of hitting it just right. And SNN is also doing pretty well, or just as well.
It seems that they miss at the extremes, right?
Sorry?
At the extremes, they miss the distribution at 1 and 5.
At 1 and 5, yeah, this is true.
And perhaps there is a way to fix that if there is a typical.
That's probably true, yeah. I wonder how much of that is a function of the particular distribution, like data generating process we used versus not. That's a good question, because a lot of times you'll see in a lot of these in real data that things are 1 and 5 a lot.
Yeah, exactly.
Right.
It's
So
exactly what I have in mind.
yeah,
People try to be.
They hate it or they love it. Yeah.
And they may not be very representative. I think that people who have a strong feeling about something they rate.
Yeah,
and
exactly.
They
Yeah.
just watch the next movie. Right?
Exactly. Yeah.
Okay.
Yeah. Absolutely. And then we ran it with limited mnar, which is the distribution process that's become in vogue nowadays. And so you can see now that the dark blue and the light blue do not match each other as well anymore, right? There's clearly a bias in the distribution. And again, USVT does pretty terribly, right? You can see that it's basically just predicting the mean. Now, soft compute's still doing okay, but there's a bias, right? You can see a clear difference between the light blue and the dark blue. But it's still decent, but not nearly as good. And then the SNN is doing pretty well too. Again, the light blue is quite hidden behind the dark blue. So you can see that once you start messing with the missingness pattern, things start going haywire. Okay, now we did the causal mnar, as I call it, where we broke the conditions for needed for these algorithms, the state-of-the-art algorithms. So again, USVT does poorly, but now look how badly soft compute's doing. it's kind of just predicting 1 for some reason, right? 1,600 of that. So it's doing awfully. And I wouldn't show it to you if it didn't work, but so synthetic is still doing pretty well. So it's interesting because if you look at this missing this pattern, you just looked at it empirically, the dark blue here, and you looked at the dark blue here, you couldn't tell one's worse than the other, right? But underneath there is a big difference in the way they run, but if you just look at it empirically, you couldn't tell. But still, it has this huge effect on soft impute.
Sorry, just one question. In soft impute, it's not the case that you have to use other covariates to.
No. So we're using the trick where you run MCAR twice,
Okay.
and you debias it that way.
Okay, that's okay.
Yeah. Interestingly, for USVT, we did it with the 2 MCARs, and it does even worse. So this is with it just doing the regular version of it. And so hopefully this convinces you that it's very, very important to think about the missingness model in these kinds of problems. Because firstly, recommendation systems are everywhere. And we're using them for movies, products to purchase, news articles now, and we're seeing how much that's affecting the way people behave and purchase and so on and so forth. And it's also in data sets. I think I learned from, Raul and I learned from Victor recently that in the US Census data, like 40% of the values in certain crucial columns like income are missing. Right? So it's extremely, and it's clearly not missing at random. People are not providing it for some underlying reason. Right? So we need to think about these things very, very carefully if you're going to make policy decisions or any sort of causal inference on top of this. Now, just to give you an idea of the type of sparsity patterns that we do see in practice a lot. So the recommendation systems one, so this is pulled from George Chen and his author's work on the right here, which are 2 canonical data sets. You can kind of see that this block sparsity pattern kind of shows up. There are a few things that are rated by a group of people and a group of movies are always, or items are always rated, and other things are not rated at all. Right? So you have this block sparsity pattern. And then on the top left here is a caricature of how something good like that could look like. So why would you observe everything, a full set of columns? That kind of models, as I'm sure a lot of you know, if you go into like Hulu or Netflix or something, you will have to rate 20 movies at the start that everyone has to rate. And then based on that, they use that as a warm up or a hot start to what types of things they should recommend to you. So that items there kind of correspond to those things that everyone has to rate when you first come in. But this is where hopefully it can convince you that, you know, it's much more than recommendation systems, matrix completion. So one is, so synthetic controls is very much an example of this, where for the top row, you're missing something from a certain point onwards. You can also think of this as David was talking about in this talk last week, as dropouts, right? So there's some people who carry on in say an experiment, and some people drop out for some reason, and then you're missing their data after some point of time. Other things are, say, staggered adoption. So there are people you observe it for a while and then you don't observe anymore because they have been intervened on, but there are these like staircase type things that happen. A similar thing could be happening in, say, like discontinuity design, because you start giving people intervention when they hit something, like they get to a certain age or they have a certain income, something like that. So again, you might have that's another example of what I call staggered adoption. And then also something like sequential decision making, where each time step, let's say there are 2 actions you can pick. So you pick one action, and then you, at another time step, you pick a different action. And that's obviously going to give you this block sparsity pattern because everyone is observed under 1 of 2 interventions at any particular time. Right? And that's also quite popular in a lot of modern systems where you do switchbacks. So you run an intervention for a while, you take it away, you run an intervention for a while, you take it away. And so you kind of see this kind of block sparsity pattern over time as well. So hopefully this convinces you that a lot of times you can think of your problem as a matrix, and based on the particulars of that particular experimental study, observational study, it naturally induces different kinds of sparsity patterns. And I think what's interesting is a lot of them can be thought as like block sparse. Okay, so now let's think about a causal perspective to think about those kinds of problems. So this is what we have termed causal missing not at random, or CMNR. So this is a model for missingness that we will allow for. I'm going to walk through this slowly. So recall that Aij in our model is Uij U transpose Vj, right? So it's a latent factor for the unit and a latent factor for the item. You're taking the transpose of that. So all the U's and D's, let's just call them your latent factors. Your D, which is the thing that decides which of the entries you see, can be any arbitrary function of these latent factors. Right? So hence you have the arrow pointing from you in the DAG, you have an arrow pointing from the UVs to D. And now the Y's, which are your outcomes, we know from our parametric model that they're a function of UV and epsilon, right? Because Yij is equal to Aij plus epsilon ij. So if I tell you UV and I tell you epsilon, the Y's are completely known, they're deterministic, right? So Y is affected by both of those things. The key requirement that we make is that D, which is your interventions in some sense, or the things you see, is independent of Y, your outcomes, conditional on the latent factors. Okay, so we allow for things like the minimum probability of seeing something being 0. We allow for to be correlated between which entries you see. So if I tell you that you observe something for a user, you observe them under movie 1, that means deterministically they don't watch movie 2, for example. That's allowed. And obviously D and Y are correlated, right, through the latent factors, right? So that's what we call like confounding in our case, as I'm sure everyone here is familiar with. The key thing we're not allowing for is an arrow from epsilon to D, right? So one way of interpreting this is that you can make decisions on what to see and what not to see based on the expectation of what the rating will be. But you can't make it based on the rating itself. Right? So that's kind of the limitation. So let's say you had a bunch of like, let's say coin flips, right? And based on your probability of the bias of the coin flip, you can decide which ratings you want to see, but not once you see the ones and zeros. You can't decide based on that. Right? So that's what, in my head, I think of as selection and latent factors. Any questions? It's kind of the key causal thing that we assume. Okay. So now I'll explain the method to deal with that works with that kind of missingness pattern, or the selection and latent factors, synthetic nearest neighbors. And so it combines two ideas. It combines ideas from K nearest neighbors, or what we call collaborative filtering. So the idea is simple. So let's say I want to fill in this missing value, this question mark, okay? And so, and let's say the 1 and 4 are observed for entry for, let's say, movie 1 and movie M. Other entries, other rows that have similar values to you, at least the things that are observed, right? And so let's say in this case where it's not K nearest neighbors, 1 nearest neighbor, you're just finding one row that's similar to it. So this row, the bottom row is the most similar because it has the 2 entries in the end that are exactly the same. So one estimate for the question mark is whatever the entry was for the last row, which is 4. So that's how nearest neighbors work in a nutshell. And then we are very familiar with synthetic controls, so I'll go through very quickly. The idea is that you have some entries here that are missing. What you do is you learn a linear model between the pre-intervention periods, right? Your Y and YZ3. And then you use that and the post-intervention data, the units that remain under control, and you'll use that to fill out M hat. That's how synthetic controls works. And then in general, Abadi et al., they propose that you should use convex regression with this to ensure that it's regularized and also that you're not extrapolating. There's been recent work started by Amjad Shah Shen in 2017, and then it's been corresponding afterwards. Basically a method called robust synthetic controls, but it's really the same thing, except now instead of regularizing using convex regression, what you first do is you do it using principal component regression. So you learn your linear model by first doing PCA on Z3 and learning a linear model there, and then using that to get your M hat. Right? So it's basically the same thing as regular synthetic controls, except the way you regularize your fit is different. Okay. So now how we're going to combine these two ideas of synthetic controls and nearest neighbors to come up with synthetic nearest neighbors. Okay, so let's say this is the entry we want to fill out. So Aij. Okay, that's going to be our target causal estimate, right? And just recall, right? So we said Yij is equal to Aij plus epsilon ij, and expectation Yij is equal to Aij. So what do? We look at what we call the neighboring columns for row I and the neighboring rows for column J. Right? So that's given by the NCI and NRJ. So you look at everything that's filled up. Right? So that gives you a subset of the rows and a subset of the columns. Okay. And from there, what you do is you look for a fully observed submatrix. Right? So that's what I call the anchor columns and the anchor rows. Right? So this fully observed submatrix is what I call X. Right? And now you see, I'm sure you can see it's starting to look like synthetic controls, right? Because you can think of the X as your pre-intervention for the donor group. The top part is your pre-intervention for the target unit, and so on and so forth. Right? So it's starting to look a lot like synthetic controls, and that's exactly what we're going to use. So what we're going to do is, except the difference with synthetic controls is that rather than fit one model, we're going to fit k models, and that's why we call it synthetic nearest neighbors. And I'll go through the algorithm in just a second. So what you do is you break up your x into k subgroups. For the moment, let's say 2. It's going to create 2 nearest neighbors, synthetic nearest neighbors. So y is the outcomes are observed for row I in your anchor columns. X1 and X2 are partitions of your matrix X into 2 sets of rows. And then the X tilde 1 and X tilde 2 are the things that are observed in column J. Okay. Any questions? Okay, so now what you do to create your first nearest neighbor? You do PCA on X1. You learn a linear model between Y and the low rank approximation of X1, beta hat. You use that on X tilde 1 to get A hat, ij1. And you do that with PCA of X2 to get A hat ij2. Right? So you can think of each of those things as one synthetic nearest neighbor that you're creating from this set of rows.
Can you interchange the rows of y and x here?
Rows of Y and
The
X?
rows of y and x.
Oh,
You're calling the first row y and the last column x.
yeah.
You can go the other way around.
Absolutely. So it's about which is the target row. So in this case, the target row is I. So then the entries in row I will be Y. But if, let's say, the last row becomes your target row I, then that becomes Y and the rest of it becomes X.
But you're saying like flip the role of the rows.
Yeah.
Oh, you transpose the matrix, you mean? Oh, absolutely. Yeah, absolutely. And we'll talk about which way you should do it in a second. Yeah, we'll talk about which way you
I
should.
guess that in some cases it would be obvious, and in some cases
Yeah.
it may not be.
Yeah. So in essence, what you want is you want to have your matrix be as square as possible, like the number of rows and number of columns being as square as possible. That's the high level intuition of what you want, at least theoretically speaking.
Sorry, so having your matrix meaning X, like having the whole complete submatrix, or having X2 be as square as possible, like X1 and X2.
X1 and X2 be as square as possible. And the number of these X1 and X2s we should have, we'll talk about that relative scaling in a second. Yeah. Because it'll scale with the minimum of those 2 dimensions, your error. And then how do you produce your A hat ij? You simply take the average of the k synthetic nearest neighbors. So that's the algorithm. Cool.
So what is the benefit of doing like synthetic nearest neighbors? Having k larger than 1?
Yeah.
PCAs in each, like, because it's linear, right? So you take an average to make them different.
So the reason is that the reason is the X tilde 1, X tilde 2 are noisily observed, right? And so if you just take it with you learn a single model and you use that to fit A hat ij, you're somehow not killing the bias or the noise in the X tilde 1, X tilde 2. By taking averages of things, it removes the noise. Yeah, it's for the variance. That's exactly what it's for.
Although in some sense, I mean, would a different way, in some sense, is the splitting basically then playing the role of basically forcing your beta coefficient to spread, your beta coefficient to sort of spread, and so would a different way to basically be run this, but basically force your beta coefficient to load on a lot of entries, right? To sort of not concentrate the weight too.
Yeah, you could have done that.
That's an interesting point. I haven't thought through that. Yeah, that could work. Because you could argue somehow that in some sense, one long beta hat, you're learning k different vectors of this long beta hat, and you're taking the inner product.
Exactly.
But somehow enforcing that on the whole thing in a clever way, it's doing the same thing.
Right.
Yeah.
Yeah, like sort of straightforward, like like
That's an excellent idea.
straightforward.
We're going to try that. Yeah. Ron?
The partitioning of the complete submatrix, is that going to be an automated process?
Yeah. So we just do it randomly. A lot of time, it doesn't have to be a complete submatrix. You can have many different blocks in different places to learn it. Yeah. And so what are the key assumptions we need for identification estimation? One is we just need a large enough X in some sense. And let's say this matrix X is of dimension k cubed by k squared. Then what you need is you should create k of these submatrices, each of size k squared by k squared. And the errors that I'm going to present to you in the next few slides are going to scale with k. Okay. So this is what we need. This is like an instance-dependent thing. If your data doesn't happen like this, you're not going to be able to estimate AIJ well using synthetic nearest neighbors. The second thing we need is that the x1 and x2 are well conditioned in some sense, basically saying that the smallest singular values of them in expectation, not the noisy version, in expectation, are sufficiently large, right? Because as we know from linear regression, you need the small singular values to be sufficiently large to be able to have good estimates. Right? And there's this notion of well-balanced spectra has been explored in various ways in various different contexts. So in matrix completion, there's a notion of incoherence. I think in the panel data literature, as I've learned from Anna and Victor and Alberto, has been this notion of strong factor assumption of pervasiveness. It's a similar idea. Somehow there's enough spread of the signal amongst the singular values that are low rank. And the last one is what I call span inclusions, which basically requires that the expectation of y lies in the row span of your xk, in expectation of xk. Doing that is really what motivates you being able to learn a linear model. Right? Because if that didn't exist, then there's no linear model that expresses y in terms of x. And then we're going to transfer this model from y x1 to x tilde 1. Right? To be able to do that, what you need is that the expectation of x tilde k lies in the column span of expectation of xk. Because think of it as a special case where expectation, let's say xk's are all 0. Then you can't learn any model, right? Because all of your data is just 0. And so this is kind of allows you to transport your model across different observations. Okay. And then here's the finite sample result, is that using the synthetic nearest neighbors, if you have those assumptions, then this is how your error scales. Scales is basically the linear model beta that you learned. Think of it as the max over all the k betas that you learned, the one norm of that. The rank of your matrix A, R3 over 2, and then scaling with 1 k half, 1 over k half. Okay. And just as a sanity check, we said, well, does this sparsity pattern exist if you have missing completely random data? So, and how many things you need to observe to be able to do this? So let's say the probability of observing something is n to the negative delta. Then you will know with high probability that your error will scale as delta to the 1 over 12, which is clearly not optimal, but is like a first pass of showing that even with decreasing number of entries being observed in an MCAR setting, you at least still get consistency. But this can clearly be improved significantly. Then this is your normality result, is that if you normalize it by your a hat ij minus aij by square root k, because you're taking k nearest neighbors, right? So square root k is the right normalization. And you divide it by the variance, and I'll explain what the variance is, then you get a standard normal. So this is the confidence interval. And what is sigma tilde k? It's a function of the betas, the true beta, and which is estimated consistently using beta hat, and then the sigma ij's, which is the second moment of epsilon. Okay, and we'll talk about how to estimate sigma square ij in a second.
In the previous slide.
Yeah.
The one row, the beta.
Yeah.
Depends, like you can probably figure out exactly like amount of that, or do you? So what is it exactly? It's over all the possible.
Think of it as that you learn k different models. Okay. Think of the maximum of those k models, or actually you should think of it as the average one norm of those k models. That's what this is.
Okay.
Yeah, it's really the average. And then one thing I found interesting is that I was thinking, what's the best sparsity pattern for synthetic nearest neighbors? What's the way I would want my data to look like to be able to compute everything with the minimum number of entries? You kind of want this L to show up, right? Because then you're using the same observed entries to learn over everything, right? Because the last few rows correspond like are your donors, and then you have the same sort of common observations across all different items, and you can use that to impute, right? So with just n times k square plus m times k cubed entries, you can accurately impute all n times m entries. So it scales linearly in n, which is an m, which is what you want. And I was thinking this is maybe some way we should think about experimental design. If you can think of your data as somehow reduce it to matrix completion, is you kind of want to collect data that looks like an L, and you can fill up the rest of it. So at least that's some intuition for how one could think about experimental design in these kinds of settings. Any questions? Okay, so I'm going to skip the experiments because I think it's And I'm just going to talk about something that I found quite interesting, which is how do you do heteroscedastic variance estimation using causal matrix completion? So we want to build confidence intervals, we have to be able to estimate the sigma square ij, right? Now, if they're heteroscedastic, then we need to be able to play structure on this to be able to estimate it, right? And as Rahul and I learned from Whitney recently, this is something called like the incidental parameters problem. And we have to deal with it. It's impossible to deal with it if you don't have structure in the problem. So one way of dealing with this is to assume that the sigma square ij's are also Lorentz inherently. So then here's an algorithm to learn it. First, let me tell you why that helps. So what is let's say I do a coordinate-wise squaring of your observed entries y squared ij. In expectation, that's the a square ij plus sigma square ij, right? Then let's define the matrices A, which is your matrix of the latent signal. Let's think of matrix S as the matrix of the squared variances. And then H is your expectation of y squared ij. You can easily show that the rank of H is bounded by the rank of A squared plus the rank of S. Actually, not S squared, just rank of S. Right, so if the sigma squares are low rank matrix and A is a low rank matrix, then H is also a low rank matrix. And that's the key structure we need to be able to learn stuff, right? So what's the algorithm? So the first algorithm, this is a simple three-step algorithm. First, you estimate A at Aij. So you see you run synthetic nearest neighbors and Yij to get a good estimate of A hat ij. Then you estimate A square ij plus sigma square ij. So what you do is you square your observations, then you run synthetic nearest neighbors on that to get an estimate of A square ij plus sigma square ij. Then to get sigma square ij hat, you take your matrix, you take your estimate of A square ij plus sigma square ij, and you minus it from A hat ij squared. Right? You can see algebraically why that would make sense. Right? Any questions?
And then where do you plug these sigma squared? I guess just this can produce negative numbers, so I'm just wondering what can.
Yeah. So in both theoretically, the right thing is to threshold it at 0. That's a good point. I skipped that, but yeah, you should. And they can only improve your error in some sense. So theoretically it works. Yeah. And so what kind of bounds you're going to get by running something like this? So let's say you run synthetic nearest neighbors and using, you get a bound of A square ij plus sigma square ij minus your estimate is less than delta 1. And let's say A hat ij minus Aij is less than delta 2. Then how is your error for sigma square ij going to scale? Let's see. So we know by definition, this is how sigma square ij minus sigma square ij. I don't know, looks like, right? Then all I'm going to do is, in the second bound, is I'm going to plus and minus A squared ij. And then you can clearly see that this is going to scale as delta 1 plus delta 2 squared. Right? So if you can estimate A hat, if you can estimate the squared well, the second well, and also the true thing well, the mean, then you can estimate the variance well too by doing that simple algebra trick. Okay, and then I'm going to conclude.
So when the experiment actually skips, the experiment
Yeah. Okay, so for the conclusion, so one thing I'll say is that people say that when people think of matrix completion, think of recommendation systems, but hopefully through the one slide I showed you about different sparsity patterns, there are many different problems that we thought of as matrix completion. Other ones I think are worth thinking about that maybe come more from statistics and ML, but I think people here should also be thinking about is one called reinforcement learning. So there's something called Q estimation reinforcement learning, which is a way of learning the reward for a given state in action. A lot of times people assume that Q is also low rank. So you can think of that as a matrix, right, where you have states and actions, and the entry is Q, SA. And you're observing very sparse entries of it, and it's clearly going to be missing out random because some policy is driving which of these things to observe, right? Like a Bellman update equation or something like that. So here again, you could think of this using something like matrix completion to think about it. Another one that's kind of interesting is multi-binomial logic models. So here you can think of someone having a skill level, say Wi, and you can think of Aij as the fraction of times j will beat I. Right? So it's Wj over Wi plus Wj. Right? And again, if you can estimate Aij well, it's quite easy to show that you can estimate the Wi's and Wj's well. So you can recover the skill levels. Another one that I find interesting is time series analysis. So a lot of one of the key canonical data structures you take with the time series is you create the Hankel matrix out of it, or the page matrix. Basically, you cut it up and you put it into a matrix in a similar way. So you take your, let's say L is hyperparameter, you take your time series of size T, and you break it up into L different columns or row, right? And then you create the Hankel matrix or page matrix. And you can show that this matrix, which I found very surprising, is that for any differentiable periodic function is low rank, right? And so again, and a lot of times with time series data is going to have a lot of missing values. And so you can think of matrix completion as a way of imputing values for a time series that's a lot of missing data. Okay, so I'll end. I think one phrase that I like is, causal inference is a missing data problem. That's what a lot of people say, at least in econometrics and statistics. And matrix completion is also a missing data problem. I think they really are deeply connected. I think there's a lot to be done there. I think one thing that's interesting is there's a lot of, there's a one-to-one mapping between a lot of the canonical words. So like confounding can be thought of as missing random data. Different kind of observational experimental studies have induced particular sparsity patterns in matrix completion. And estimating different kind of counterfactual outcomes just correspond to imputing specific missing entries of your matrix. Thank you. That's it. Thank you very much.
I have a quick question.
Yeah.
So would it be fairly straightforward to throw in covariates if you have them?
That's a very good question.
You have them to the X matrix.
So you could just append it, for example, if you, so that's one thing you could do. A lot of times that does help. When you have very, very few observations, it helps. The second you have enough outcome data, like for the outcome of interest, then covariates tend to not help very much as just an appending. I think one very interesting problem you could think about is that, so I showed you the causal DAG where the selection latent factors, right? But let's say you didn't want to assume that whole. And so let's say you thought of the covariates as instruments. And so maybe you should think of taking your original outcome matrix, projecting onto the matrix of instruments, and then doing your matrix completion there. So it's a different kind of estimator. I think that's super interesting to think about to get different kinds of exogeneity assumptions you need. I think understanding the role of covariates is super interesting and unresolved.
For the simulation study you have any like rule of thumb, like how much data you need for this to work? Because I mean, obviously, you have a lot of data.
Yeah.
But if you have like 100 observations, you still do this or 50 observations. How much do you need?
So we have basically found that if the number of observations you have, this is the heuristic, but like number of observations are square, where R is your rank, that generally works pretty well. So like the rank that I think was 10, and so 100 observations approximately was good. But this is the,
But just like
yeah. So how's your question?
Oh yeah, so I was wondering a little bit about like sort of choosing the nearest neighbors in the procedure. Is there like a prescription for how you do that?
Choosing which rows are the nearest neighbor, you mean?
Choosing the submatrices to impute from, I guess.
So you want a fully observed submatrix, right? And then within the fully observed submatrix, so far we just randomly partition it. Because randomly partitioning it gives you can show with high probability then that the linear span inclusion will hold.
Got it. That makes sense. And then another question is sort of like at a high level, like I'm thinking about like, for example, like sparse estimation, there are like deterministic properties of the design under which you can do sparse recovery, like this like restricted isometry property or something.
Yeah.
And I wonder if like thinking about the like soft impute type methods, like if there are deterministic properties of the observation pattern, which could allow you to recover.
Yeah, that's a question. There's a lot of work being done like this, yes, like by theoretical computer scientists, where they think of you can think of it as a graph, right? So you have rows as being a set of nodes, columns as being a set of nodes. And then if you have an entry observed, then you have an edge between, like in this thing, right? And then they have deterministic properties about, I think, where the graph is an expander or something like that, then it's recoverable. And I think a lot of the optimization-based techniques, those are the type of deterministic sparsity patterns that they require. But my understanding of it is relatively limited.
Cool, thank you.
Cool. Anything else? I'll stop there. Cool. Thank you very much.
Cool.